Okay, so here we are in section 1.6, and we're trying to determine whether or not this statement here is true or false, and we want to provide some justification for our answer. And so the way I've started this, and this is just the way I kind of think about the problem, but the way I started this is I rewrote the inequality that's in the statement so that the y is by itself. So I just subtracted 1 from both sides. And the reason I did that is because I recognized that from algebra. If I was to write y equals x squared minus 1, I remember that the graph of that is just the parabola shifted down by 1, which is this graph right here. And so then it's pretty easy to draw y greater than x squared minus 1, which would be the shaded region above the parabola. And I did that just to kind of help me get a start in thinking about the problem. In terms of that shaded region, if I read my quantified statement, that would be for all x, there exists a y that is in the shaded region. So in other words, if I pick an x value at random, maybe I pick this x value, can I get myself into the shaded region from that x value? Yeah, I wouldn't want to move down in the y direction, but if I move up in the y direction, as long as I go up far enough, I'll be in the shaded region. Or if I pick another x value at random, maybe this x value. Well, if I pick that x value, I am already in the shaded region. So it seems reasonable, just with a little investigation, that no matter what x we have, we can find a y that's in the shaded region. And in fact, the way I wrote this inequality tells us how to pick the y. The y has to be greater than x squared minus 1. So I might pick y equal to x squared plus 1, and that fits the condition of being greater than x squared minus 1. So if I go with that and come back over to the left side here, I'm going to write out my justification for the problem. Since the quantifier for all is on x, that means x could be any real number, so I'm going to write that, let x be any real number. And the quantifier there exists is on the y, so I'm going to pick a y, and I already wrote over here how I'm going to pick that y. And then I'm going to take this y value and substitute it into my inequality right there. So if I do that, then all that's left is one or two basic steps of algebra. So if I just remove the parentheses, x squared plus 2 on the right, and then if I take that guy and I subtract x squared from both sides, I have a very simple inequality that is obviously true. We can say that's always true. And so because of that, the quantified statement is true. And this was just the way that I thought about working the problem. You may like my explanation with the graph if you want to use a graphical explanation. You may want to jump straight to the formal explanation or the formal proof, which I did on the left side there, or maybe you have a combination of the two or something that you've thought of on your own. But whatever you do, there does need to be some kind of justification and not just an answer when you look at these.